radiotherapy treatment planning also onto the same CT scanner machine. And since it requires longer exposure time at higher kV than needed for general radiography, these have been charged with heavy-duty rotating nanotube with higher thermal capacity and smaller focal spot. These tubes are air-cooled with current value up to 600 mA. CT tubes are oriented in the gantry with long axis perpendicular to the fan beam to avoid heel effect. And some CT tubes are grid controlled for pulsed radiations to reduce radiation dose. This is not the grid which we are talking about in the X-ray. And beam collimation at 2 points, one close to the X-ray tube and other at the detector. And collimation regulates the slice thickness. Each detector has its own collimators. And in some volume scanner, the beam is collimated through multiple slits to reduce scanner produced before striking the patient, known as the multi-slit, multi-slice CT scanner. So desirable characters for a detector: the cost shall be as minimum as possible, high absorption efficiency and high conversion efficiency. Responsiveness. Response time refers to length of time it takes for a detector to review and discard signals. And dynamic range refers to the detector ability to receive wide range of X-ray intensities with proportional output. If exceeded dynamic range, streak artifacts may occur. And gas ionization detectors and scintillation crystal detectors are used. So the principles of scintillation detectors contain these crystals, they contain scintillatory crystals. Example, cesium iodide, sodium iodide, BGO, bismuth germanate and cadmium tungstates associated with photomultiplier tubes and silicon photodiodes. So sodium iodide was used in the first generation CT scanners with photomultiplier tube. So although its efficiency is 80 to 90%, now this is not used because hygroscopic in nature and require airtight containers, and they have the afterglow. Means you know what is a scintillation. So when the X-rays falls on the crystal, it emits light. So that light is detected by the photomultiplier tubes, amplified in the photomultiplier tubes, and the output signal is given to the computer electronic system to generate the images. So the major problems with the scintillation detectors is the hygroscopic nature of the crystal. So that absorbs the moisture in the room. So then once it absorbs the moisture, then the scintillation properties of the crystal will become ineffective and the crystal will get damaged. So we have to keep the humidity under very strict control, and not only that, the crystal needs to be completely air sealed so that no moisture can get inside. So if there is any gap or any damage in the sealing of the crystal, then that can result in wrong information being saved and bad image being formed. And these crystals, some of the X-ray energy which might have trapped in the crystals, and it can come out as light at a later phase. So that is called an afterglow. And long-term efficiency is less as they require time-to-time calibration. And cadmium tungstate is the most commonly used in CT scanners. You recently ceramic detectors have come into picture and very commonly used. So these scintillation detectors are still in use in gamma cameras and positron emission tomography cameras. Xenon gas detectors. These arrays are a series of highly directional xenon-filled ionization chambers. as X-rays pass, ionization takes place and the charge ions are collected as electric current at the electrodes. Used mainly in rotate systems because of long linear structures. Their efficiency is about 50 to 60%. So we can see that they are much lesser efficient in comparison to the scintillation detectors. Coming to the image reconstruction, in computer tomography, a cross-sectional layer of the body is divided into tiny blocks. Each block is assigned to a number proportional to the degree that block attenuated the X-ray beam. This block individually is called a voxel. The three-dimensional block is called a voxel. The linear attenuation coefficient is used to quantitative attenuation. So n equal to n0 e raised to minus mu x. If the block of material with different attenuation coefficient placed in the path, then the equation will become n equal to n0 e raised to minus mu1 plus mu2 plus etc. mu n into x. So this mu is the attenuation coefficient. So if there are materials of different attenuation is there, then the equation becomes little more complex. The values of mu1, mu2, etc. cannot be determined without additional information. So an algorithm is a mathematical method of solving a problem. The iterative method, the method of assumption, comparison with the measured values and correction to bring two into agreement, and then repeats the process over and over until the assumed and measured values are same or within acceptable limits are called iterative method. So we assume a value, compare it the measured value, correct the assumed value to be similar to what we measured, then repeat this process many times to bring the assumed value to be same as the measured value. So this is called iterative, repeated iterations. So three types of iterative methods are simultaneous iteration, ray by ray iteration, point by point iteration. With incomplete data, iterative methods are better. So if our acquisition data is less, we have less information from the imaging system, then iterative methods are better because it will iterate further and again to reach the desired value for the image formation. So it can compensate for the missing information by means of iteration. Back projection is also called summation method. This is one of the oldest methods of image reconstruction. The object is scanned from the different direction, and when the transmitted ray from the two or more projections, they produce a crude representation of the original object. So this is something like what we were seeing, like how we were getting three-dimensional images or three-dimensional information by acquiring 2D information in different planes or different angles. Analytical method, they are more commonly used nowadays, and the 2D Fourier analysis and filtered back projection analytical methods are the ones which we use most commonly in the CT scanners. The basis of Fourier analysis is that any function of time or space can be represented by sum of various frequencies and amplitudes of sine and cosine waves. And filtered back projection, similar to back projection, except the image is filtered or modified to exactly counterbalance the density which causes blurring in simple back projection. The mathematical filtering step involves convolving the projection data with a convolution kernel. Faster as compared with iterative reconstruction, and both are accurate if projection data is complete. So here you can see this is the original image. So we are getting a profile From that, the noise signals are filtered to finalize the image. So when we get the back projected image, it is like this. So when we filter the signal to remove the unnecessary signals which are present in that, so we will get a better quality image. So the amount of filtration and back projection. So remove the signals, back project it to form the original image. So further remove the signal, further filter the signal, then remove it. So once the image quality is within acceptable limits, we can stop the filtered back projection kernel. So various filters can be used to emphasize the different characteristics in the CT image. So one is lag filter when there is no noise in data, and Shep-Logan filter when incorporates some role of inherent frequency, reducing higher frequency noise in the final CT image. And then harming filter where it has even more pronounced high frequency roll off with better higher frequency noise suppression. So in the filtration actually helps us to remove the low signals, low energy signals, and when we have high frequency signals, these advanced filters help us to remove the noise from the signal. So this is an example of how the frequency, the noise is removed using the different filters. So you can see that amplitude versus frequency graph of different filters. So how the filtration works. So you can see that accordingly the image quality, contrast or resolution becomes better. Algorithms for helical CT, where the data interpolation is performed by a special computer program called an interpolation algorithm. So it can be an interpolation or an extrapolation. In interpolation, estimation of the value between two non-values is done, and extrapolation is estimation of the value beyond the range of the non-value is done. Like we have a graph, x and y axis, we have information of the y-axis varying from say 5 to 20 of the x-axis data. So we do not have information below 5. So there we extrapolate following the trend which is there between 5 and 20. So in interpolation it is like we have 0 to 10 and 15 to 20. So we do not have information from 10 to 50. So that is interpolation. Connecting from 10 to 15 is interpolation, and when we do not have data below or beyond some value, that interpolation is called extrapolation, extending the information which we have to acquire the or predict the information which is beyond or below is called extrapolation. So here you can see this what is shown as the Hindu mark, that are the non-values. So we do not have, so while we are drawing this graph connecting these two x's, we will know the value of this point. That is interpolation between two values. And further extending the graph and getting this point is extrapolation, where we have only one value below and we want to know what would be the value here at this point. So that is extrapolation. So there is 360-degree linear interpolation and 180-degree linear interpolation, where the plane of reconstructed image interpolated from data acquired in one revolution apart is 360-degree linear, and interpolation of the value separated by 180 degree. Half a revolution of the X-ray tube is 180 linear interpolation. And 360-degree linear interpolation, blurring in the reformatted image is more pronounced. And when we do the 180-degree linear interpolation, results improved Z-axis resolution and greatly improved reformatted image. So it is similar like, so we are interpolating, we have this X and this X. If we have more X's in between, then we connect all that, this value will be more accurate. If we have lesser value and we are connecting two far off points, the intermediate value which we are getting by connecting those may not be as precise as when we have more number of points to connect in between. So this we know that we are plotting graph, the basic principle of plotting graph. So same, when we have information for one full circle, we have lesser information, and when we have information for half a cycle, so we have more information or double the information. So that will result in improved image. And image display, a CT image displayed is consistent of a matrix of picture elements called pixels. Each pixel represents the linear attenuation values of X-ray at the particular point of body. And pixel is a 2D display of a voxel. Commonly used matrices are 256 into 256 or 512 by 512 or 1024 by 1024. So this is a pictorial display of how the pixels and voxels are arranged in the space volume element. The image matrix, the CT scan format consists of many cells, each assigned to a number and displayed as an optical density or brightness level on the video monitor. So pixel, each cell of information called pixel, and numerical information contained in each pixel is the CT number or Hounsfield unit. It is a two-dimensional representation of corresponding tissue value, and the three-dimensional or the volume element is the voxel. CT number is defined as the relative comparison of X-ray attenuation of each voxel of tissue with an equal volume of water. So see, this we have seen, CT number is K multiplied by mu rho minus mu water divided by mu water. So this we change from the CT numbers are defined for -1000 to +1000 with the water values compared with the tissue or tissue and water equivalent Hounsfield units or the attenuation coefficients. So this represents the attenuation coefficient as well as the density. So these are interrelated. More dense, more attenuation will take place. Less dense, less attenuation will take place. And windowing is a system where the CT number range of interest is spread over the full grayscale available on the display system. And window width means the total range of CT number values selected for grayscale interpretation. And it corresponds to contrast of the image. And window level represents the CT number selected for the center of the range of the number displayed on the image. It corresponds to brightness of the image. Window width corresponds to contrast and window level corresponds to brightness. So Hounsfield unit, different Hounsfield units, we have seen this before also. So there are hard bone and soft bone also. So -1000 through 0 to +1000, the Hounsfield unit varies. So we will have more of discriminatory power to identify tissues of varying density, which are near in densities also. When it is spread across a larger scale. So we have seen this before. So there can be spatial information, how accurate the spatial information is recorded and shown. And there can be artifacts which can reduce the image quality and the detail. So if there are more information and more signals which are causing blurring, then contrast and sensitivity, how good the bright area and the dark area can be identified and appreciated, and how good the system in identifying a deficiency or defect in the system. So, and the noise. So additional information which is embedded into the imaging system, which will reduce the image quality. So here you can see that the slice thickness, MAS, metrics, all those things will the operating parameters such as all these will affect the image quality characteristics. So it is the visibility of the diagnostically important structure in the CT image. Quality is defined in terms of resolution. Resolution has two components, spatial resolution and contrast resolution. So spatial resolution of a CT unit is the ability to display separate images of two objects that are very close to each other. And contrast resolution is defined as the ability of the CT unit to display the distinct images of the area that differ in density by small amount. So contrast resolution is superior in CT than conventional radiology, and spatial resolution is inferior. Contemporary units have resolution up to 15 line per centimeter. Resolution is very much related with two other things, that is quantum motile or noise and patient exposure. Contrast resolution is increased by decreasing the noise, which requires more number of photons, resulting in more patient exposure. Spatial resolution requires smaller pixel size, which requires smaller voxel and correspondingly smaller slice thickness. For smaller slice thickness, we need more exposure to get sufficient signal, resulting in more patient exposure. Coming to the artifacts, undesirable optical density on an image, in general, we can call it as an artifact. Systematic discrepancies between the CT numbers in the reconstructed image and true attenuation coefficients of the object is called artifact. There can be different causes and different appearances of artifacts. So it can be physics based, patient based, scanner based, and there can be helical artifacts. So physics based because of the beam hardening, partial volume effect, photon starvation, undersampling, and patient based because of metal artifacts or patient motion, and scanner based because of the detector sensitivity and mechanical instability. And we have seen the helical artifacts where the rotation takes place and the corresponding display and imaging system. So beam hardening, I think we will stop here for today. Can we have class tomorrow, 2 to 3?
Yes, ma'am. We can have. Yes, ma'am.
Okay, then we will stop it here and continue tomorrow 2 p.m.